So let us begin with the next lecture by Gordon. If what is written here in the program is true, it will be first the fourth lecture and then the third lecture.
No, I'm going to change that order. All right, so this is really the third lecture, and it's perturbation theory. And beyond. Beyond means K. So Roland just told us something about K. I'll try to explain what that K really is here. And maybe we need to remember some of the things that were happening last time. So I want to compute the susceptibility of the four-dimensional phi to the fourth model, the lattice version. And so this chi-n, which depends on two parameters, g and nu, and also the number of components of the field n. We're on a torus of side length L to the n. That's what this n is here, and we want to let n go to infinity ultimately. And what we saw last time was that this can be expressed in terms of in the following terms. Let's see, and then what did we have? We had the second derivative of Zn at 0 in the direction constant field, 1, divided by Zn of 0. So this was a little lemma that I derived last time. And what is this Zn? Zn, it's a function of a kind of external field phi. And it was the expectation with respect to a Gaussian measure C, which has covariance minus Laplacian plus m squared inverse of z0 of phi plus zeta, where z0 of something, well, z0 is just e to the minus v0 of lambda. And v0 of lambda is also v0. It's a function of the field, and it's the sum over all x in lambda of 1/4 g naught phi x to the fourth plus 1/2 nu naught phi x squared. And this g naught here, this g is g naught, and this nu is nu naught plus m squared. So this was an elementary bit of calculus in order to derive this formula, and it was supposed to reveal to you that if you want to compute the susceptibility, what you really need to know is this function Zn. And so we were concentrating on what that function Zn was. And the way that we were approaching it was we took this covariance C and we divided it up into a sum of covariances that had desirable properties. Finite range was one of them, and estimates was another. And these estimates were supposed to be capturing the idea that when you integrate out covariance by covariance, you're actually integrating out the fluctuations on larger and larger scales. So this Gaussian expectation over there, EC, is really a composition of many Gaussian expectations, and we want to do them one by one. And of course, we're interested in what a typical one looks like, so one in the middle. And so we introduced this map, Z, which goes to Z plus, which is E plus, where this plus is the short form for J plus 1, theta of Z. Okay, so that it's Cj plus 1 is what this plus stands for. So it corresponds to just doing one of these integrals and feeding in a reasonable z and trying to figure out what is the z plus that pops out. So we've got this map, and a very interesting kind of z to apply the map to is, so take z to be e to the minus v of lambda. And what we would like to do is to calculate the renormalized potential. So if z starts like this, we'd like to write z plus as e to the minus v plus. That is going to be, in general, a very complicated function, v plus. And what perturbation theory does is it extracts from v plus the part which looks like v. So theta, yeah, so theta is a function of phi. So it's basically telling you it's a convolution. It's saying that the z plus is the convolution of the measure e plus with z. Right, so what perturbation theory does is it tells you what is a good approximation to z plus written as e to the minus v, I'm going to call it vpt for perturbation theory, which is of the same form as v, or at least a sum of only relevant and marginal monomials. So then you want to find vpt, which I'll call it plus, such that the expectation of e to the minus v of lambda is equal to e to the minus vpt plus of lambda. This is as formal power series, equivalent as formal power series to an error of order v cubed. And that's a problem I wrote down the solution to last time, and actually other people have written down the solution to that problem as well. It's given by the cumulative expansion. You want to take the expectation of an exponential, and the first order in v, that's the exponential of the expectation. The next term involves a covariance. I discussed this last time. And what I want to do now is say that you find, after some simplification that I don't want to discuss here in detail, because although I've got 2 hours, I have a lot of things that I want to say, that the formula that vpt is given by the following. So I want vpt, maybe I should say up here that vpt plus of phi and lambda should be the sum over x in lambda of some gpt of phi x to the 4th times 1/4 plus 1/2 nu pt phi x squared plus upt. And actually in the Euclidean model there's also a Laplacian term, a Laplacian of phi squared term, but I'm not going to include that here because it's not particularly important for what I want to say. So what I want to say is that you can compute what these constants are, and GPT, well, because of the simplification, I'm going to say, I'm going to write a bar for the, instead of the initial g in v and the GPT, I'll just write g plus bar for the sort of representative of GPT after the simplification. And it has this form. One minus n plus 2 over n plus 8 beta g bar plus eta prime g bar minus c prime g bar squared. The primes are there because I'm going to have another version of eta and xc that are more important, and they won't have a prime on them in a moment. So what are these things? So the g and the nu are the parameters in v. So this v that I'm starting with here is a local polynomial with the g 1/4 g phi to the 4th plus 1/2 nu phi squared. That's what the g and the nu are. I should really put bars on them all. And so g plus and nu plus are a version of GPT and nu PT after some simplification of the equations, which is innocent as far as the behavior that we're going to be computing is concerned. These coefficients beta and eta prime, c prime depend only on the covariance. You would have exactly the same equations for the hierarchical model or for the Euclidean model. The only difference is that the covariance that you're integrating with respect to is different, and that will affect the values of the constants. So beta depends on j, and it's n plus 8 times the sum over x of wj plus 1 squared 0x. I'll say what w is in a moment. So what w is it's the sum of all of the covariances that have been seen so far in the previous integrations. So wj is the sum I equals 1 up to j of ci. It's all of the earlier covariances. And if you were to consider the limit as j goes to infinity of this term, for example, then what you would end up with is the full covariance, right? The full initial covariance, because you would have all of the covariances adding up, and that would reconstruct the covariance decomposition to give you the full covariance. This would be the L2 norm of that, which in the massless case would be divergent. It's the bubble diagram. And so these two terms are each wanting to diverge as j goes to infinity, but their difference remains finite, and it converges to some positive number, beta infinity, which depends on the mass, but remains bounded as the mass goes to 0. So that's beta. So that's, this diagram here. This one is this diagram. And so eta prime is just a Wick term. Eta prime is equal to, well, it depends on j, and it's just some constant that depends on the number of components times cj plus 1 on the diagonal. So these are pretty routine calculations to carry out. That's why I'm not doing it in detail here. We saw some of these numbers showing up in Anti's talk. I think there were some numbers like 144 or something. They look a little bit different than my numbers because I'm using 1/4 in front of the phi to the 4th term, and Anti didn't. But this is what happens if you have a general number of components. All right. So this covariance here scales like L to the minus 2j. That was an estimate that came in the covariance decomposition. The covariances were designed to have that property. So in this recursion relation, actually psi will be the same. So we have these exponentially small terms, and this is where we do the scaling. So there's been no scaling up until this moment, but to get rid of those exponentially small things, we'll do some scaling now, and let mu j be L to the 2j times nu j. So then we want to just multiply this equation here by L to the 2 times j plus 1, and that will get rid of these exponentially decaying coefficients. So then we get the equations, same one for g, and for mu, this is the L squared that Alessandro was asking about at the end of the last lecture, 1 minus 1 L squared times mu, 1 minus n plus 2 over n plus 8 beta g plus eta now has been multiplied, eta prime has been multiplied by L to the 2j times g bar plus minus 6c times g bar squared. So these two terms now are order 1. Any question about these equations so far?
There is still g bar in the first parenthesis.
Yeah, thanks. Right, well, if this was the whole story, then we would basically be done. We could do the computation of the susceptibility and compute the critical exponents. So let me show you how that works. Because essentially what we need to do is to show that we can perturb around this solution that I'm about to present. So first of all, before we get to that, let's just solve these equations. So this is very elementary. The equation for G bar there is just, this equation shows up in many, many contexts, and it's a simple recursion relation for G, which you can solve. And you find that G bar J for large J behaves like G bar 0 divided by 1 plus G bar 0 times the sum I equals 1 up to J minus 1 of beta I. And that beta I is a difference, right? Here's the formula for beta. And so when you do the sum, it's a telescoping sum. And so you just get the last term. So as m goes to 0, what this becomes is simply 1 over the bubble. So this bubble here is the sum of all of these betas. All right, so it's just, like I say, it telescopes. You end up with the thing I was talking about earlier. So this bubble diagram is just the sum over all x in lambda of the full covariance C0x squared, which is a function of m squared. And it diverges logarithmically as m goes to 0. We're in 4 dimensions. This is behaving, like 1 over x to the 4th, except there's a mass term as well. So this thing behaves like 1 over the log of m to the minus 2, maybe with some constant, which you can compute. And this will happen here as long as j is greater than or equal to the mass scale. So the mass scale is defined by m squared L to the 2 mass scale equals 1. If you remember in the estimate for the covariances arising in the decomposition, there was this L to the minus 2j factor, but then there was also a factor of 1 over 1 plus m squared L to the 2j to whatever power you wanted it to be, reflecting the fact that once the scale gets large enough, the mass kicks in and begins to give very strong decay of the covariance. So after the mass scale, these betas are basically 0, because the new covariance that gets added in is so small. And so this just basically stops evolving at the mass scale. Another way to see that is up here, that after the mass scale, beta becomes essentially 0, and so G plus is G. All right, so Gj is behaving basically like 1 over j up to the mass scale, and then it stops. So that's the solution to the G equation. What about the mu equation? Well, the mu equation is it's a linear first-order recursion relation, so it's easy to solve. The one issue is that we don't actually know what the initial condition is. This is connected with the question of what is the critical value. So, we don't know what the critical value is. We were trying to compute it. And so a very good idea for this equation is to write it backwards and then solve it with a final condition that it be 0. So if you write it backwards, you just solve the equation for mu. You take everything else over to the other side. There's a very helpful factor of L to the minus 2 that shows up. And so you write the mu equation backwards. And you solve it with the final condition that it should vanish. And here's the solution. It's explicit. this pi is a product. So it's the product from, let's get it right here, k equals j up to L of 1 minus n plus 2 over n plus 8 times beta k gk bar. You see, we know what g is because we've just solved the g equation. So everything on the right-hand side of this formula inside the big sum is known to us. So it's all explicit and very elementary. How does this product behave? Well, we're interested in a situation where the g is going to be small. And so this is actually can be well approximated. So all of these approximations that I'm about to write down now are very controlled approximations. This is just elementary stuff. 1 minus beta k gk bar to the power n plus 2 over n plus 8. All right, to first order in g, that would be accurate. And now, if you go back to the g equation, you see that 1 minus beta g is just a ratio of, 2 subsequent g's. You just divide that equation up there by g, you get g plus over g is 1 minus beta g. So when you take this whole product, it's a telescoping product now, and you get g bar L plus 1 over g bar j to the power n plus 2 over n plus 8. So that's going to be important.
How you have chosen this L?
It's anything at the capital L is just some number fixed greater than 1 for the moment.
I was thinking about small L, but the lowercase L. I understand. It's just something.
Yeah, it's the summation index. All right, so in particular, as j goes to infinity, mu j bar will go to 0. This sum is very convergent. These g's are well under control from here. These pi's are, well, the 1 over pi is actually growing, but there's an L to the minus 2 factor here, which is, to L minus j. This exponential just makes everything converge. There's no problem with this sum at all. And so, in particular, mu bar j goes to infinity as j goes to infinity, goes to 0 as j goes to infinity. And in fact, mu bar j is order of L to the minus jm plus times gj bar. This factor, this good power of L comes from the fact that these coefficients eta and xc begin to decay exponentially after the mass scale. Yes?
The xi-L are just functions of the covariance j plus 1?
Yeah, so I didn't write down what xi was, but I wrote down a couple of the other ones somewhere. Where are they? I don't see them anymore. But yeah, so I wrote down beta and I wrote down eta. Xi comes from this diagram, for example, or this diagram. But yeah, it's just from functions of the covariance. They're completely explicit things. Yes?
Are you implicitly assuming that the mu infinity is finite for solving?
It's 0. Yeah, so I'm choosing I'm choosing that final condition for the recursion relation. And that is determining what the critical value is at this perturbative level. In fact, so the critical value is just nu bar of 0. This is all perturbative still, but it's nu bar of 0, which is the same as mu bar of 0. So the perturbative critical value is nu bar 0, which is mu bar 0, which is this sum. So it's sum L equals 0 to infinity, L to the minus 2j, 1 over this pi, 0L minus eta L GL bar plus psi GL bar squared. So you can calculate it to order G, order G0, and you find that it's given by n plus 2 times the covariance, the full covariance on the diagonal, times G0. So this determines the critical value perturbatively. Now let's go back to our original problem of trying to figure out how does the susceptibility diverge at the critical value. So here's a calculation of that. So gamma is the critical exponent for the susceptibility, which is now going to have a logarithmic correction. Okay, so there should be a log here. So let's go back to our formula for the susceptibility, because that's our starting point. It's right here. And let's suppose now that we've managed to control all these renormalization group maps iteratively, so that at the final scale, the Zn is just given by e to the minus Vn. So suppose that Zn is approximately e to the minus Vn, where Vn is the local polynomial which has been produced, whose coefficients are given by the G bar and the nu bar at scale n. So we go back to the formula for the susceptibility here, and we want to now evaluate it. And so I'll say that this is approximately equal to the same thing that you get by replacing Zn by e to the minus nu n, e to the minus Vn. And Zn of 0 would just be e to the minus Vn evaluated at phi equals 0, which is 1. So it's easy to take the second derivative of e to the minus Vn and put, in the direction of a constant field, and put the field equal to 0. So this, you just calculate it, and it's equal to minus nu n. Times lambda. Actually, that's important. Cancels the lambda that's down below. All right, so it's just a calculation. You're just differentiating the exponential of a polynomial with respect to the field, and so that's that. So this becomes 1 over m squared minus nu n over m to the 4th. And nu n is exponentially small, right? Mu j already is going to 0. It's leaving aside what happens after the mass scale. It's already ordered g bar, and g bar is small. And nu is L to the minus 2n times g bar. This mu. So this goes to 0. And so the limit, as n goes to infinity, of the susceptibility is just 1 over m squared. So, in other words, here's what we know from this calculation, assuming that all of this perturbative business that we've been doing is accurate, and we have all kinds of remainder terms to be concerned about eventually, but for the moment, let's forget about that. So what we get is that chi of G0, nu 0, which depends on m squared, plus m squared, it's the new zero that got produced over there, is equal to 1 over m squared. And we've calculated the new zero that does that job. Now think about what happens as m squared goes to 0. As m squared goes to 0, this diverges. Well, this m squared will disappear, and this will actually, in fact, it will approach some limit, nu naught of 0. And we will have calculated then the critical point in, for the infinite volume theory this way. So the critical point, the nu c, is this nu 0 of 0. There's all kinds of errors that we've neglected at this point, but anyway, this is what's happening. And so how does that help us to actually calculate the critical exponent? How is chi blowing up? What we'll do is we'll find a differential equation. So this is the only differential equation in my talk. It's a first order ODE. But we'll calculate the derivative of chi n with respect to the initial condition. And up to this approximation, chi n is just given by this formula here. So m squared is fixed, and we're varying the initial condition. So we want to know how does nu n respond to a small change in nu naught. So this is going to be, up to that approximation, what is it, 1 over m to the 4th times the derivative of nu n with respect to nu naught. And that you can just compute, because nu n is just this equation without the L squared, essentially. This part doesn't matter because it doesn't depend on nu naught anyway. So what you get if you, by the chain rule, if you differentiate nu n with respect to nu naught, is you just get the product of all of these factors over all of the scales. So this is just equal to what I called pi 0 n. Right? Pi 0 n was this product. And it's just an elementary calculation with the chain rule that tells you that this is what you get. So that's
m to the 4th power.
m to the 4th, thank you. Yeah. So that's this. So this is going to be equal to g bar n, or n plus 1. I mean, let's not worry about that, divided by g bar 0 to the power n plus 2 over n plus 8. And we've seen what this gn is, right? N is definitely after the mass scale. We're letting n go to infinity with fixed m squared, so it's after the mass scale. And so g bar n is going to be given by 1 over the bubble, which is blowing up logarithmically. And m to the minus 2 is the susceptibility. So what this is equal to is minus 1 over chi squared. Not 1 over, just chi squared. Chi is 1 over m squared. And there's a log now of chi. So if you pay attention, what you find is that it's the log of 1 over chi to the power n plus 2 over n plus 8. That n plus 2 over n plus 8 is this n plus 2 over n plus 8, which arose in the coefficient of the mu recursion up there. So that's my differential equation. D chi by, I haven't been careful about writing limits as n goes to infinity here, but d chi by d nu naught is given by this formula, so you can compute chi. And what you find is that chi so you solve to determine chi. Maybe I won't write it down. So that will tell you what this critical exponent gamma is with the log correction. Okay, the log correction comes up because of the appearance of the log here with that power. So on the perturbative side, that's the way the calculation goes. Any question about that? Yes?
Has to be
approximate the derivative, no? I mean, how do you do that?
Yeah, this can all be done carefully. Yeah. So this calculation hopefully gives you a hint as to how it would be possible from having a flow of the renormalization group, that is, knowing how these renormalized potentials evolve over scales, how that knowledge leads to a calculation of a critical exponent. And the other critical exponents that I mentioned yesterday can be calculated using ideas that are quite similar to these ones. All right, so all of that was based just on perturbation theory. I just assumed that when I integrated e to the minus v over a scale, I got an e to the minus a new v, which had the same form as the old one, and that's not true. So we need to do some work in order to deal with that aspect. And that's where the non-perturbative coordinate comes in. So I need some setup to describe, some language in order to just say what it is, what kind of space does this non-perturbative coordinate live in. So we need to just take a few moments to introduce some formalism here. So we've seen many times the introduction of blocks. So we're going to divide up our torus lambda, which has side length L to the n, into blocks of size L to the j. So this is an example of a block B and script Bj. So script Bj is going to be the set of all j blocks. And a polymer is a union, a finite union, well, it has to be finite, but it's a union of j blocks. So I've got all this colored chalk here. Blue was the bad color? I forget.
Yeah, blue is for blue.
Okay, no blue. Let's try yellow. So that's an example of a polymer. Okay, so it doesn't have to be connected. This is X, which is in the set of polymers at scale J that are constructed out of these J blocks. So for X in P, I'll tend to drop the J if it's not playing a big role. Often it'll be two scales in play, and one of them will have no, there'll be no indication of the scale, and the other one will have a plus to indicate that it's the next scale. So for X, a polymer, the set of blocks in X is denoted like this. So this is blocks in B. And the same thing for polymers. Sometimes we want to fix a particular polymer and look at what's happening inside that. So we look at the blocks inside a given polymer, or the polymers inside a given polymer. And then I'll define the script n to be smooth functions of the field. So phi is in R n to the lambda in general. What I mean by smooth, there's a lot of flexibility there. You can take them to be analytic functions, or you can take them to have some number of derivatives, at least 10, I think we want. Now, I want to consider maps from polymers into N. So I want to consider maps of the form, well, I'll call it F, which maps polymers into N. So let me give you an example so that you know what is an interesting one of these functions. F of x could be, for example, e to the minus v of x phi, where v is the sum over points in x of v of phi of x. Okay, where v is a local polynomial of the type that shows up in these models. Right, so to every polymer x, we associate a function of the field, which is this function. So maybe I should really write dot here to emphasize that it's considered to be a function of the field. Now, I want to define a product on such functions. It's called the circle product. So if I'm given two of these maps, what I want to do is to define another one, which is the product of these two. As follows. So it's supposed to be a function that takes a polymer into a function of the field. So what is that function of the field going to be? It's the sum over all y's polymers inside x of f of y times g of the complement of y in x. So basically what this does is it takes x and it divides it into two pieces in all possible ways and evaluates f on one piece and g on the other piece. And then it sums over all of the ways that you can do that. It's a kind of a convolution. It's a very nice product. It is commutative and associative. It has a unit element. It's scale dependent. I want to emphasize that because it's defined in terms of polymers, which are scale dependent objects. So if I define this product on one scale, it's not exactly the same as on another scale, although it has the same formula. So the identity element is 1, and it's defined by 1 of x is equal to 1 if x is the empty set, not to be confused with a field, and it's 0 otherwise. All right, so if you check what happens when g is the identity up there, the only contribution is going to come when y is equal to x, in which case you'll get f of x. And so it works. Here's a little lemma about this product that will be important for our calculations. So if f and g factorize over blocks, so what I mean by that is that f of x, and same for g, would just be given by the product over all the blocks in x of f of b. An example of an f that factorizes over blocks is this e to the minus vx. Right, that e to the minus vx up there is the product over the blocks in x of e to the minus vb. So that's a good example of what one of these f's or g's might be. Then there's this beautiful formula that the circle product is just given by the product over all blocks of f of b plus g of b. Okay, do you see the proof of that? It's very easy to prove. Just expand. Expand the product on the right-hand side. You'll get a sum over terms where, the terms are distinguished by, when do you take an F and when do you take a G. So you'll be summing over all of the polymers that are inside X, where you take F on that polymer and G on its complement, and because of the factorization, it works. Okay? So the factorization hypothesis makes this work. So the proof is just expand the right-hand side and invoke this factorization hypothesis. It's very elementary. All right, so that was an introduction of some kind of algebraic structure. And now I want to put that into our problem. So let's return to our problem. Which is that we would like to be able to apply this map that takes Z to its expectation repeatedly. So we want to iterate over scales the map. Z goes to Z plus, which is the convolution of Z with the expectation. So maybe I should put a plus here. We know Z naught. It's e to the minus v of lambda. So initially, Z naught of lambda equals e to the minus v naught of lambda. And I want to write that as a circle product, but in a kind of a silly way at first. So I'm going to write that as e to the minus v naught circle identity evaluated at lambda. And our goal is going to be, if I have a Z, which is of the form e to the minus v circle something, which might be more complicated than this identity, can I write Z plus as like e to the minus v plus circle something new, which is that previous coordinate brought on to the next scale. So I want to say, given Z of lambda equal I circle k of lambda, find v plus and k plus such that Z plus, which is the expectation, so Z is I circle k of lambda. Maybe I should put the lambda here for emphasis. I want to compute this Z plus, and I'd like it to have the form I plus V plus circle k plus of lambda. In other words, I want to preserve this form I circle k for Z as we advance the scale. Now I, you should think of as e to the minus v, always. All right, even though it is for the hierarchical model, otherwise there's this extra non-local stuff that you have to carry around. But I don't really want to get into that. It's a kind of Taylor's theorem, this theorem, which is going to produce the k plus, a good k plus, in the sense that it's taking care of all of the errors that take place in perturbation theory. So perturbation theory is a kind of a Taylor approximation. And what this k is going to do is it's going to take care of all of the errors that are made in that Taylor approximation. So what do we want about this k? Here are the features that we want it to have. Maybe before that I should say what is the RG map. So the RG map for us is going to be the map that takes the v and the k that describe the initial I. So this I is a function of v. Think of it as e to the minus v, actually. That takes this initial v and the k to the new one. So there's a v and a k which describes the system at scale j. It will map to a new v, which will have something to do with perturbation theory, of course, and a new k that describe the system at the next scale after one scale has been integrated out. This is going to be completely explicit and simple. And it's related closely to this VPT, this bar map that I talked about before, you know, those flow equations that we were studying at the perturbative level in order to compute the critical exponent for the susceptibility. This one is also explicit, but I wouldn't call it simple. And it's controlled using estimates. So what do we want that k to satisfy? Well, we'd like all of these errors in perturbation theory to be third order in G. So if k starts off third order in G, we would like the new k to also be third order in G. So if k is order of, I'll call it v cubed, so v is the polynomial here. In particular, it includes g, which is really controlling also mu, as we've seen over there. Then I would like k plus to also be order v cubed. And I also want it to be a contraction.
V or V plus?
V plus, it's okay, yeah. And I also want it to be a contraction, so I want a contraction, which means that if I take the derivative of k plus with respect to k, that should have norm less than or equal to 1. Now, I haven't said anything about norms yet, but you know, we're starting to do analysis now, and so we need to have a way of deciding how big is k. Already here, you know, when I say that k is order v cubed, I need a norm on k in order to make that statement. So that's part of the story that I'm not going to enter into now, and if I have time at the end of the next lecture, then I will say something about it there. But what I want to try to illustrate in the time I have left, which is later, I think, right? We have a break now, right? Yeah. Is how is it possible? How can we arrange this? What is the obstacle to overcome, and you know, how is it possible? If we succeed, so maybe I'll finish off with this today, for now, until half an hour goes by. Let's just say what would happen if we succeeded. So if we succeed, then what happens at the final scale? That is, we manage to carry this out and get all the way to the final scale, scale n. Zn of lambda will be In circle Kn of lambda. But remember, this circle product is scale dependent. And at the final scale, there's only one block. And so in this sum here, when x is lambda, the only thing that y can be is empty or everything. So there's only two terms in this sum at the final scale. This is In of lambda plus Kn of lambda. This In of lambda should be third order according to what we desire. And it doesn't play a role in perturbation theory calculations, right? I mean, I was only doing second order calculations when we calculated the exponent for the susceptibility previously. We didn't have to worry about what was happening at the third order level. And this will just be e to the minus Vn, which is the thing that we used in order to do those previous calculations. So if we build the V plus on perturbation theory, the Vn will just be the final one of those perturbative polynomials, and that's what we used in order to do the calculation previously. So we'll be done. All right, so that's a good place to stop now, and we'll continue in half an hour, I guess. Thank you.